take a look at this pattern. We're taking the binomial x plus y and raising to exponents that increase by 1 on each line. We want to look at some characteristics here. We have x plus y to the 1 power is x plus y squared is x squared plus 2xy plus y squared, and so on. All right, notice first of all the number of terms in the expansion of each one of these. X plus y squared has 1, 2, 3 terms involved. X plus y cubed has 4 terms involved. X plus y to the 4th has 5 terms involved. So it seems to be the case that the number of terms in the expansion is 1 larger than the exponent on the binomial, and that is always the case. All right, notice also that we start the expansion with the first term of the binomial raised to an exponent which is identical to the exponent on the binomial. So x plus y to the 4th starts with x to the 4th. X plus y cubed starts with x cubed. X plus y squared starts with x squared, and so on. All right, then what happens is that in the next term we have, now we're only looking at exponents here, we have a term involving an exponent which is 1 less than that. And then in the next term we have x to an exponent 1 less than that. And then an exponent 1 less than that. And then x to the 0 power could be thought of as appearing here. So in succeeding terms, the exponent on our first item in the binomial is decreasing. Now look at the exponent on y. We start out with a term involving no y factor. We could think of this as y to the 0 power. In the next term we have y to the 1 power, and then y squared, and then y cubed, and then y to the 4th. So the exponent on the second item in the binomial is increasing by 1 as we go through this pattern. Okay, so we have the number of terms is 1 greater than the exponent, and we have this ascending and descending exponent on our 2 items in the binomial. Well, what about coefficients? Well, it turns out that the leading coefficient is 1 for all of these, and then the next coefficient happens to correspond with the exponent you see in the expansion. So here we have 4x cubed y, and here in the expansion of x plus y to the 5th we have 5x to the 4th y. And we'll talk about other coefficients in a little bit, but that's one that we can pick off right away. Oh, another characteristic having to do with the exponents in each term is this. That notice now this is the 4th degree expansion. We have x to the 4th here. We have x cubed y, but look at the sum of the 2 exponents. We have 3 and 1, 4. In the next term, 2 and 2, 4. In this term, 1 and 3, 4. In this term, 4. You see, so all of the terms have as their sum of exponents 4. And for the 5th degree expansion, all of the terms would have as the sum of exponents 5. Now notice a symmetric quality having to do with the coefficients. And we talked about the leading coefficient is going to be 1 in all cases, and then the next coefficient is going to correspond with the exponent. All right, notice this also, that there's sort of a symmetric quality going on with the coefficients. That here in the 3rd degree expansion we have 4 terms, and here's the distinct middle of those 4 terms. Well, going out from the middle we have 3's as the coefficients of these terms, and then 1's for the coefficients of these. And now with the 4th degree expansion there are 5 terms, so there is a distinct middle term, but going from that middle term outward we have 4 and 4, 1 and 1. And then in the 5th degree expansion we have 6 terms. Here's the middle of that pattern, and going out from the middle we have 10's, and then 5's, and then 1's. So we have a symmetric quality involved with those coefficients. So all of those things are going on. We have all of those patterns happening. So we know right now then that if we take x plus y and raise to the 12th power, we know how to begin the expansion. It's going to be x to the 12th. The next term is going to be 12x to an exponent 1 less than this, and then y will make its appearance as a factor. And then in the next term, we don't know what the coefficient is going to be, but we do know that we're going to have x to the 10th and then y squared. You see, and this decreasing idea on the exponent of x and an increasing idea on y, and the total of these is going to be 12 for all of the terms. We also know that the second to last term in that expansion is going to have a coefficient of 12, and the last term is going to have a coefficient of 1, and it's going to actually be 1y to the 12th power. Okay, so we know all of those kinds of things. Now let's talk a bit about the coefficient generally in a binomial expansion. It turns out that that is what the binomial theorem is all about. In the x plus y to the 12th expansion, find the coefficient of the term involving x to the 7th, y to the 5th. And the binomial theorem allows us to make that calculation. Now I'm using a specific example here. We can generalize this in a little bit, but the specific example is this specific expansion. All right? Now to generalize it, we would say it's the expansion of x plus y to the n power. You know, something like that. But this is very specific. Now by the binomial theorem, that coefficient is given by this notation and this calculation. The notation here is red. This is the combination of 12 things taken 5 at a time. And another way to show the exact same notation is to do this. This says the same thing. And the calculation associated with this is 12 factorial over 12 minus 5 factorial times 5 factorial. Now let's see where all of this comes from and where we're going with this and how we can manipulate this idea. By the way, the notion of combinations is heavily involved in the study of probability. And it's something that we'll get involved with at another time. But just for the time being, let's just understand that it's a particular notation and this is its correspondence. All right, now the 12 appearing here corresponds with the exponent on the x plus y. So that's where that comes from. And it turns out that the 5 here happens to be the exponent on the y. You see, the exponent on y, the second part of the binomial expansion, you see. Okay. Now, let's make the correspondence between these two. We have 12 factorial. The 12 corresponds here with the numerator, you see. And then in the denominator, we have a couple of items. One of the items is the difference of these two, factorial, and the other item is this second rascal, factorial. Okay, so all of that is going on. Now, it's only a matter of experience that allows us to remember this and understand it well. I don't recommend that we go and try to memorize this. We'll get enough practice with it so that the memory will be very efficient very shortly. All right, let's make the calculation. Let's see, we have 12 factorial is 12 times 11 times 10 times 9 times 8 times 7, and I'm going to stop right there. I know that there are some more factors, but I'm seeing that in the denominator I have 12 minus 5, which is 7 factorial. So I have 7 factorial times 5 factorial. Now 5 factorial I'll go ahead and expand as 5 times 4 times 3 times 2, and I could write the 1 here, but I don't need to. Now I stopped here at 7 factorial because I recognize this, and all of the factors involved there will take out all of the factors involved here. And now we're looking for other cancellation opportunities. I see 5 times 2 is 10. We'll cancel with the 10 upstairs. I see 4 times 3, 12, and those factors will cancel with the 12 upstairs. So we just multiply 11 times 9 times 8, and we find the value here to be 792. Okay, let's go through some other calculations involving this combination formula. And then we'll get back to the idea of the binomial expansion. Let me just show you some manipulative opportunities here with this combination business. Now, with the combination of 8 things taken 2 at a time, you know that the numerator of this fraction is 8 factorial. In the denominator, we have 8 minus 2 factorial times 2 factorial. Okay? So we would end up writing, let's see, 8 times 7 times 6 factorial. We would stop right there. And in this denominator, we would have 6 factorial and then 2 factorial, which is simply 2 or 2 times 1. Now, the 6 factorials will cancel, and I have 8 times 7 over 2. Now, here's what I want you to notice about the pattern. That in the numerator, once I've performed this calculation of cancellation, I have 2 factors starting with 8. In the denominator, I have 2 factors as well, but this is really just 2 factorial. Now, this is no idle coincidence with the 2 that appears here. In the combination of 8 things taken 2 at a time, you can make the calculation, you can make this cancellation very quickly just by saying, okay, the numerator is going to contain 2 factors starting with 8. So just write 8 times 7. The denominator is 2 factorial, or simply 2 here in this case. All right, now the calculation, let's see, the 2 and the 2 goes 1, 2 and the 8, 4, 4 times 7, 28. All right, let's use that trick and perform the calculation here. Now for this one, let's see, the numerator is going to contain 3 factors starting with 10. So in the numerator we have 10 times 9 times 8. And in the denominator we have 3 factorial. So that's 3 times 2 times understood 1. And now we go through and make the calculation. Let's see, we have 2 into 2, 1, 2 into 8, 4. 3 into 3, 1, 3 into 9, 3, 3 times 4, 12 times 10, 120. All right, here's another one. We have the combination of 8 things taken 6 at a time. Uh-oh. This tells us, if we're going to use this trick, it tells us that we have in the numerator 6 factors starting with 8. Gee, that doesn't seem to give us a great deal of efficiency. Let's just expand by our definition of the combination idea, the combination formula. We would have here in the numerator 8 factorial. In the denominator we have 8 minus 6 factorial, and then we have 6 factorial. Oh, well, this is nice because we have the 6 factorial here that can cancel with what's upstairs. So we'll have 8 times 7 times 6 factorial over 2 factorial times 6 factorial. Now I want to write it like this because these are canceling. And now we have a situation that's identical to the situation over here. We have a couple of factors up here and 2 factorial downstairs. Well, what's going on here? Well, it turns out that there is a symmetric quality having to do with the combination idea. It kind of goes along with the symmetric quality involved in the coefficients and the binomial expansion. And it has to be that way, doesn't it? I mean, the binomial expansion contains that symmetric quality, and we're talking about ways to generate those coefficients that have that quality. So it's no wonder that we would have that quality here with our combination formula. Now, so it turns out then that if you want to get the efficiency out of using that little trick, then what you would do is just rewrite this and say this is equal to the combination of 8 things taken. Now here's how it's calculated. It is 8 minus 6 here. So this becomes 2, you see. The combination of 8 things taken 2 at a time, just like we had over here. And then we can go through that little pattern of 2 factors in the numerator starting with 8 and 2 factorial in the denominator, which we see here. So we get the same result that we did before. Let's use the idea on this one. Now notice the combination of 10 things taken 7 at a time. Now over here we had the combination of 10 things taken 3 at a time. And it turns out that these are equal to one another. So what we would do is we would just adjust this and say, oh, this is the same thing as the combination of 10 things taken 10 minus 7 or 3 at a time. So then we would have, let's see, in the numerator, 3 factors starting with 10. 10 times 9 times 8. In the denominator, 3 factorial or 3 times 2. And multiplying, we find the value to be 120 as expected. This array of numbers is called Pascal's triangle. It is an array of numbers that is sort of self-generating. I want you to notice that 1s appear along this part of the triangle and 1s appear along this side of the triangle. And the interior numbers are generated by adding items that are above. That here we have 1 and 1 for 2. And this 3 is just the sum of 1 and 2. And this 3 is 2 and 1. You see, and in here we have 1 and 3 to give 4, 3 and 3 to give 6, 3 and 1 to give 4, and then a 1 on the outside. And then for this line it would be, well, let's see, a 1 on the outside, 1 and 4, 5, 4 and 6, 10, 6 and 4, 10, 4 and 1, 5. You get the idea. If we want to generate another line on Pascal's triangle here, then we would write a 1, and then 1 and 6, 7, and then 6 and 15, 21, and 15 and 20, 35. Then 20 and 15, 35. 15 and 6, 21. 6 and 1, 7. And then a 1 on the outside. Now notice the symmetric quality involved in the numbers that appear in the array. That is, from the center of the triangle like this, we have this symmetric quality. Does it remind you of something? Well, it should. These entries in Pascal's triangle are actually the coefficients involved in the binomial expansion. For example, if we look at the expansion of a 5th degree binomial, the coefficients will be given by these values in Pascal's triangle. Now notice 1, 5, 10, 10, 5, 1. Come over here. We have in the 5th degree expansion of x plus y, we have as coefficients 1, 5, 10, 10, 5, 1. You see, so using Pascal's triangle, we can actually generate the coefficients involved in binomial expansions. Now, that works pretty well at the relatively low levels. That is, if we're talking about, let's say, an exponent of 9 for the expansion, x plus y to the 9th power, then what we would have to do is expand Pascal's triangle down to the point where we had a 9 as the second entry, you see, and those entries then along the horizontal level here, this row would correspond with the entries for a 9th degree expansion. Well, it certainly wouldn't help us if we were expanding beyond that. We would have to use our binomial theorem idea. All right, let's go through a couple of expansions here. Sometimes the items involved in the binomial are not just x and y or a and b or something like that. We can have some coefficients other than 1 involved with the two items in the binomial. So let's at least begin the expansion here. Now with a 5th degree expansion, we know that there will be 6 terms. All right? We know that the first term is going to be this first item to the 5th power. We know that the second item is going to have a coefficient which is 5, that is corresponding with this, and then we're going to have x to an exponent which is 1 less than this, and then in our previous discussion we talked about our second part of the binomial appearing to an exponent which is 1. Well, the second part of the binomial is just this 2y business, so we'll have the appearance of 2y. You see, and then for the next term, and from Pascal's triangle or from the binomial theorem, I know that the sort of naturally occurring coefficient is going to be 10. And then we have x to an exponent 1 less than this. And then the second part of the binomial, 2y, appears to an exponent which is 1 larger than this. This is 1 and then this is 2. And as a cross check, I know that the sum of these two needs to be 5. Okay, and the situation continues on. All right, so this is just the first 3 items in that expansion. Now, to continue further, though, we need to simplify in these terms according to what we see. That is, we have 2y here times 5x to the 4th power. So the 2 has to be multiplied times 5 to give 10. So this is 10x to the 4th y. And then here we're squaring 2y. So squaring the 2 gives 4. 4 times 10 is 40. And then x cubed y squared. And then on we go with the expansion. So the idea is that we have a naturally occurring coefficient, and then we have some extra factors may occur by virtue of raising the separate parts of the binomial to certain exponents. When a minus sign is involved in the binomial, it will cause an alternating sign pattern to occur. Now we can see it in a couple of different ways. You can rewrite this as x plus negative 2y like this to the 5th power. And now negative 2y is playing the role that 2y played up here. So everywhere I see a 2y, I could write a negative 2y. So this would become negative, that would become negative. And when I expand, I would be multiplying negative 2 times 5 to give a negative 10, you see. And then over here, though, the negative 2y is squared, so it would cause this to be positive, and a positive result would occur. And in the next term, it would be cubed, and I'm cubing a negative value, which makes it negative, so the next term would be negative. So we have this plus, minus, plus, minus, plus, minus kind of pattern, just an alternating sign pattern when we have a minus sign in the middle of that binomial. Consider this one. Now the difference in this one is that there is no y. There's no letter in the second part of the binomial. So, but we follow our nose through it just like we did before. That is, in making the expansion, we say, okay, the first term is going to be x to the 4th power. We know there are going to be 5 terms also at this point. And then we have plus, and then this will appear, then there is a naturally occurring coefficient of 4, and then x will appear to the 3rd power, and the second part of the binomial will make its first appearance. And I recommend that you do that. And then for the next term, let's see, I'm going to look over at the Pascal's triangle to tell me about this naturally occurring coefficient. So I'll look over there at the 4th level and I see that it's a 6. Okay, so it's a 6, and then x will appear squared, and then the second component, the second part of the binomial, will appear squared also, increasing exponent on that second item. And then the next item is 4x, and then negative 3 appears cubed. And then the negative 3 appears to the 4th power. Okay, let's come back and clean up a little bit. We have x to the 4th here. We have negative 3 times 4 is negative 12 x cubed. And then negative 3 squared is 9 times 6 is 54 x squared. Now notice no y here. There's no second letter involved here. There wasn't to begin with. There won't be down here either. We kind of get accustomed to that idea that we're going to have a second letter to an exponent, you see, and the exponents will add to give 4 in this case. But that's just not the case because there's no second letter involved. Okay, so x to the 4th, we have an x cubed term, an x squared term. Well, let's slide over. We have negative 3 cubed is negative 27. Negative 27 times 4 is negative 108. And it is x to the 1 power. And then negative 3 to the 4th power is 81. So once again, just keep track of the various components involved in every term, and you're not going to have any great difficulty with this. It is important, though, in keeping track of those things, not to try to perform any operations too soon. That's the tendency here. You want to think about all of the components sort of as separate events. You have a naturally occurring coefficient. You have the first part of the binomial raised to a certain exponent. You have the second part of the binomial raised to a certain exponent. And you just write down those components for every term. And then you come back and clean it up with the various operations. All right, here's another situation where we have the binomial theorem possibly involved, and it involves an expansion. But we're only trying to identify a single term within the expansion. Let's say that we're talking about the expansion of x minus 3y to the 14th power, and we want to write the term involving x cubed. The term involving x cubed. Well, let's see. We know that that term involving x cubed will contain a naturally occurring coefficient. I'll leave it as a blank right now. Then we're going to have x cubed, and then we have the next factor is going to be a factor composed of this second part of the binomial raised to an exponent which has to add with 3 to give 14. We know the sum of those exponents, you see, has to be 14. So 3 plus what is 14? Oh, it's 11. So the exponent here has to be 11. Okay, now what about this rascal? Well, let's see, the naturally occurring coefficient here Pascal's triangle isn't going to help us a great deal unless we want to spend the afternoon expanding it. So it's the combination then of, now remember how this combination notation took place. It's the 14 occurs here because it's the exponent up there. And now this turned out to be the exponent on the second component. Now when we expanded x and y, it was the exponent on y. Here it's the exponent on the second component. So it's an 11 right here. It's a combination of 14 things taken 11 at a time. Now let's make that calculation. Let's come back over here to the side and make that calculation. We know that the combination of 14 things taken 11 at a time is the same thing as the combination of 14 things taken 14 minus 11 or 3 at a time. And it's easier to work if we have a smaller number over here, and that's why we perform this little tactic. So in the numerator we have 3 factors starting with 14. So we have 14 times 13 times 12. And in the denominator we have 3 times 2 times 1. We have 3 factors, but it's simply 3 factorial. So I'll just write it as 3 times 2. Now 3 times 2 is 6, and 6 goes into 12 2 times. So we have this. And now we just multiply these rascals, and I believe when the smoke clears on this it turns out to be 364. So if we have 364 x cubed, and now in parenthesis, wow, I want to raise negative 3y to the 11th power. Negative 3 to the 11th power. That turns out to be negative 177,147. Now I didn't do that in my head. I can't do math that well. I have it written off camera. Okay, so we get this and then y to the 11th power. All right, and then we multiply the naturally occurring coefficient times this one, and we get, let's see, negative 64,481,508. You might check me on that. And then x cubed y to the 11th power. Okay, so that turns out to be our result. But it's important here, I think, to understand how we went through the process, how we started the process here. The term involving x cubed, you see, it all started with that idea. So the term involving x cubed has a naturally occurring coefficient given by this combination formula. And then the other term involves, let's see, the second item in the binomial raised to an exponent, which we calculate as 14 minus 3. You see, gives 11 because these have to total 14. And then it's a matter of calculating from there.